right, students, I'm going to discuss with you about a somewhat complicated concept called the gravitational potential. We've talked about a new definition of gravitational potential energy, which accounts for the fact that g, the acceleration due to gravity, changes as you get a significant distance above the surface of the Earth. We're going to talk about something called the gravitational potential, so pay very, very close attention here. Okay, all right, in Earth's gravitational field near the surface, if we consider a mass, a little point P, lifted from the surface to a particular height, okay? Now, the gravitational potential energy, assuming that h is not very great, is equal to mgh, where I'm defining h equals 0 to be the surface of the Earth. Now, the gravitational potential energy gained by the mass depends obviously on two different things. Number one, the size of the mass, which is quantified by the variable m. Number two, where it is, which is quantified by the variables g times h. Okay, the where it is part is called gravitational potential. Okay, so g times h is where it is. It's called the gravitational potential, and in physics we give it the variable name, the letter capital V. Very important. We're going to talk later about electric potential, and we're also going to use the variable V. This is a very useful quantity because if we know it, we can actually calculate how much potential energy a given mass would have if it were placed there. Okay? I want you to note that gravitational potential, or GH, is the gravitational potential energy per unit mass. Okay, right? So if you solve for GH, you divide both sides by m. V is the GPE per unit mass, and that's what it is. Gravitational potential is the amount of energy per unit mass that an object would have if placed at that spot in a field. Okay? Therefore, its units are joules per kilogram. It's an energy per unit mass. All right? Now, well above the surface, if you consider a mass lifted from the surface to point P, okay, we just found out that gravitational potential is GH is the GPE over m. Okay? Now, I'm going to bring in my more universal expression for gravitational potential energy. Okay? And I get that it's negative gmm over r, that's my GPE, divided by m times 1 over m. The m's cancel out, and I get that the gravitational potential, which I'm now calling V sub g, right here, is now equal to negative gm over r, where m is the mass of the Earth and r is the distance from it. Okay? Now, because that is the gravitational potential energy per unit mass, that's also the work done per unit mass. So negative gm over r is equal to w over m. This all seems kind of weird, but you'll see why this is all really important shortly. Okay, so I'm going to make a definition, actually a three-tiered definition of this idea of gravitational potential. It is the gravitational potential energy per unit mass on a small mass m placed at a certain point P in a field created by a mass m. It is the work done per unit mass in bringing a small test mass from infinity to point P, and at infinity, remember the gravitational potential energy was 0. It is the GPE, the gravitational potential energy, a given mass would have if placed in a certain location. That is why the units are joules per kilogram. Okay, is this all starting to make sense for you guys? The gravitational potential is defined everywhere, but it is actually a scalar quantity. It does not have direction. Super importante for you to realize that. Okay? All right, so from your IB data booklet, we get these fun expressions, all right? Your IB data booklet gives it to you in these ways, okay? This is exactly what I just came up with for you if you compare the nomenclature of the IB to the nomenclature that I just introduced things as, okay? Do you see it, okay? The work done in moving a mass, m, from point A to point B in a gravitational field, now is also, of course, the change in gravitational potential energy, but now you can think about it as the change in gravitational potential times the mass, okay? Because work per unit mass is the change in gravitational potential, okay? Very important, okay? Let's try the first example. I think when you see a couple of examples here, it'll start to make a little more sense, okay? All right, read this example carefully, and we'll do it together. Okay, so the diagram is showing various position heights above the surface of the Earth. Determine the following. The gravitational potential at A. Okay, well, you see A is one of the low values, C is the highest. Okay, the gravitational potential at A, meaning if I were to place a mass at point A, how much energy per unit mass would that mass have at that height, which looks to me to be what, 3 meters? Okay, well, it's g times h. V sub g is g times h. It's 9.81 times 3. It's 29.4 joules per kilogram. Notice how whatever mass I place there, it's not important. The gravitational potential it's the same idea in a way as the gravitational field. It doesn't matter what mass you put there. The value of that field, that scalar field, is still the same no matter what you put there, right? Okay. The change in gravitational potential when a body is moved from A to B, okay? Well, at VA, it's 29.4. I just found that. At VB, it's 78.5. It's greater, right? The gravitational potential at B is greater because it's at a higher level. Doesn't mean that the gravitational potential energy is greater. It means that the gravitational potential is greater, okay? All right, then the change is VB minus VA, which is 49.1 joules per kilogram, okay? All right, how about the work done moving a 2 kilogram mass from A to B? Well, the work done is delta V, which is VB minus VA times the mass. I got 98.2 joules. Very revealing and instructive example to know how to do this, okay? Let's continue. What's the difference in potential between C and D? Well, that's pretty straightforward if you understood what it was before. It's VD minus VC. Now we're going down, okay? And the delta V, the change in potential, is therefore negative. The work done moving a 3 kg mass from D to C, well, again, it's 88.2, okay? It's actually a negative amount of work done, okay? The potential energy of a 3 kilogram mass placed at B, well, the gravitational potential energy is given by V times M, okay? That's G times H times M, that's 235 joules, okay? That's the gravitational potential energy of a 3 kg mass placed right there, okay? Potential difference between A and E, well, it's 0. You can see that because they're at the same height. The work done taking a 2 kg mass from A to E, you can see is obviously 0 because the potential difference between them, the gravitational potential difference between them is 0, okay? You guys getting a pretty decent feel for this? Let's get moving. Let's keep going, okay? Remember that the gravitational potential is gravitational potential energy per unit mass. That's also the work done per unit mass, okay? This is what I had here before, okay? Now, a graph of gravitational potential against R is therefore going to look like this. Does this graph remind you of something? It should remind you of gravitational potential energy against R, okay? Like the gravitational field strength, which is additive, the gravitational potential at a certain point from two masses is the sum of the individual potentials, okay? The sum of the individual potentials. Study this diagram carefully and see if you understand it, okay? Negative 70, which is negative 40 plus negative 30. Once you have the potential at one point and the potential at another, the difference between them is the energy you need to move a test mass between them. The potential is independent of the path taken and is therefore what's called a conservative quantity. Okay? All this is really cool stuff. Try this example. Okay, 2 points, x and y, at distances 1 and 4 meters from a pretty big mass, 1,500 kilogram mass, could be a car. Okay? Find the gravitational potentials at points x and y. Okay? Well, at which place would it be greater? What does your common sense, your intuition tell you? Okay? Well, okay, at v sub g, the gravitational potential at x, the x and the y, it's a little bit confusing because they're both actually in the horizontal. Anyway, I got v sub g at x to be negative 1 times 10 to the minus 7, and I got v sub g at y to be negative 2 times 10 to the minus 8. Therefore, at y, it is less than it was at x. Okay? All right? Interesting. The energy needed to move a mass of 2 times 10 to the 6 kilograms from x to y. All right? I get 1.5 joules as that work. Very interesting and straightforward. Okay? All right. Let's get into some more complicated examples. These are past paper questions. Okay? Try this one. The graph shows the variation of the gravitational potential due to a planet against distance r from the center. Using the graph, estimate the gravitational potential energy of an 800 kg spacecraft that is at rest on the surface of the planet. Very interesting, okay? Okay, on the surface, r equals r. So that means that this point right here, this line, indicates the surface of the planet, okay? From the graph, the gravitational potential at that point is -5 times 10 to the 6th. That's this value right here, okay? So the gravitational potential energy is m times v, which is -4 times 10 to the 9th joules, okay? Now, the work done to move the spacecraft from the surface to a distance of 4 radii from the surface, that's going to be from here, right, all the way out to 1, 2, 3, 4. It's actually out to 5r. Note that it's not 4r, it's 5r, okay? This ends up being 3.2 times 10 to the 9th joules. Very, very interesting. Okay. Try this example. The graph shows, I'll let you read it and then you can try it. Great question. You're going to need me to go through this in class a little bit, and that's okay. I don't mind doing it, but I'll go through it here, okay? Haven't talked about gravitational potential in terms of potential wells before, but I'm going to start talking about it now, okay? If you think about this as a hill, okay, where this would be a hole and this would be a hole, and in order to get from the surface of this planet, okay, to the surface of this planet, you basically have to do work and go up and over this hill. When you get to a certain point, your spacecraft will then roll down the hill and then on its own go to that other planet, which in this case is a moon. But you've got to do work on your spacecraft to get it up and over that hump. It's the same idea as what's called a potential well. This graph is actually showing two potential wells. Here's one right here, and here's one right here, separated by a hill. The hill is the point in between right there, okay? We're going to continue this example, okay? To get out of Earth's well, the probe needs a certain amount of energy. This is the amount of energy to get to the top of the curve in the graph. So a lot of energy here, a little more, a little more, a little more, a little more, all the way to that point right there is where we need to get to, okay? Once at the top of the curve, the moon will then pull it in. It goes down the hill on the right-hand side, okay? The minimum energy to just get to the moon is the energy taken to just get to the top of that function. Once there, again, the moon takes care of the rest. So from the graph on the planet's surface, V at the planet's surface, we see this is this distance is relative to multiples of the distance between them. Okay, it's looks like negative 400 times 10 to the 6 joules per kilogram. At the function's maximum, okay, it looks like it's about, where is that? That comes over here. That's about 40, negative 40 times 10 to the 6. So since work done is delta V times M, okay, that's negative 40 minus negative 400 times 10 to the 6 times 500, which was the mass of the object. And it would take 1.8 times 10 to the 11th joules. That's a lot of energy. It takes a lot of energy to get to the moon. How are you going to get that energy? You're going to have to do a lot of work on your spacecraft. You're going to have to combust a lot of fuel to do that.